Just like in systems of linear equations in 2 variables, in 3 variables you may encounter systems that either have no solutions or infinitely many solutions. So let's take a look at what that looks like in terms of a matrix and how we would answer it. In example 6, I have this matrix. Notice it's in echelon form. So the system of linear equations, again, if we're just going to put this back into a system, it looks like this. X plus 2y minus z is equal to 0. And then y plus 2z is equal to 3. And finally, z is equal to 2. Now, this is example 4. So this is example 4. So if we go back and look at example 4, you'll notice that it's the same system that we got. Well, how many solutions did we get? Well, we only got one solution here. We got one ordered triple, and that ordered triple was 4, negative 1, and 2. Well, how did we know that? Well, z was equal to a number. We plugged it back in. We found something for y, plugged it in, and found something for x. So we have one solution, and again, that's that ordered triple of 4, negative 1, and 2. Well, let's check out what happens in examples 7 and 8. Let's put example 7 into a linear system. So we have x plus 3y minus 4z is equal to 8. Second row gives y minus 11z is equal to 5. The last row, well, I don't have an x, I don't have a y, I don't have a z. I have 0 is equal to 4. Well, 0 doesn't equal 4. This is a false statement. And if you remember, if you end up with a false statement, then you have no solution. So a false statement gives no solution. So if you end up with an augmented matrix with a false statement at the end, you have 0 answers. Your answer is just no solution. What about example 8? Well, example 8, again, let's put this as its linear system. You're looking at x minus 2y plus z is equal to 4, y minus 3z is equal to 7, and then 0 is equal to 0. Well, does 0 equal 0? Yes, that's true. That's a true statement. And when you had a true statement, you have infinitely many solutions. You have infinitely many solutions. Before, when we were just in 2 variables, we could have put all real numbers. But because we are a system in 3 variables, we need to state our solved system in terms of z. Well, what does that mean? That means that I need you to solve y in terms of z, and I need you to solve x in terms of z, and write it as an ordered triple. Well, what would that look like? Let's start with this y minus 3z is equal to 7. I'm going to bring it right over here. Now, if I have y minus 3z is equal to 7, and I want to solve for y in terms of z, well, all I do is add 3z to both sides. So in terms of z, y is actually equal to 3z plus 7. So instead of writing y, writing it in terms of z tells me I can write it as 3z plus 7. Well, what about my x? Well, my x is that x minus 2. Well, I can't write it in terms of y. I need to express it in terms of z. So do I know what y is in terms of z? Yeah, a y is 3z plus 7. So I need to write in 3z plus 7 for my y, and then finish off with my plus z equals 4. Can I now solve x in terms of z? Yes, I can. So the first thing I'm going to do is distribute this negative 2. So negative 6z minus 14 plus z is equal to 4. So the goal is to solve for x in terms of z. So combine like terms on the left, x, and then that's minus 5z minus 14 is equal to 4. If I add 14, I get that x minus 5z is equal to 18. And then if I add 5z to both sides, I get that x is equal to 5z plus 18. So now I've expressed x in terms of z, and again I expressed y in terms of z. So when I give my answer for this matrix that has infinitely many solutions, the ordered triple that it becomes is, remember, here I write my x, then I write my y, and then I write my z. Well, x in terms of z is that 5z plus 18. y in terms of z is that 3z plus 7, and then z in terms of z, that's the easy one, it's just z. So the order triple answer for this particular system that has infinitely many solutions is 5z plus 18, 3z plus 7, and then z. All right, let's look at a couple of examples that end up with special cases. So let's start with example 9. First thing, when we're solving using matrices, we write the augmented matrix. So let's go ahead and write that augmented matrix. 2, 4, negative 6, 10, next row 1, negative 1, 1, and 4, next row 1, 2, negative 3, and 7. First thing you need to do is you need to get a 1 in this top position. Well, there's a 1 in row 2, so why don't we just switch rows 1 and row 2. If I do that, I get 1, negative 1, 1, and 4 for the new first row. The second row became 2, 4, negative 6, and 10, and the last row stayed as 1, 2, negative 3, and 7. Now I need to get zeros underneath that 1. I know I need to get a 0 in both of those positions. What we're going to kind of do from now on, just to make it a little quicker, we're going to do those rows operation together before we actually write the augmented matrix. So if I want to get this 2 to be a 0, I know I can multiply negative 2 times row 1 and add it to row 2 as my new row 2. So let's see here. If I multiply negative 2 times the first row, I get negative 2, positive 2, negative 2, and negative 8. Adding it to the second row, 2, 4, negative 6, and 10. I get, in the end, negative 2 plus 2 is 0, 2 plus 4, 6, negative 2 plus a negative 6, negative 8, negative 8 plus 10, positive 2. But I'm not going to write the augmented matrix yet. I fixed this to be a 0, but I want to make this a 0 before I rewrite it. Well, again, how would I do that? Well, if I multiply row 1 by a negative 1 and I add it to row 3 and get a new row 3 from that, well, that's going to give me a 0 in that last position. So negative times row 1, I get negative 1, positive 1, negative 1, negative 4, and then row 3 is 1, 2, negative 3, and 7. If I add those together, you get 0, 3, negative 4, and then this is positive 3. So this is my new row 3. So we just did 2 steps in one, so we didn't have to write the augmented matrix again. So here's my new augmented matrix. Row 1 did not change. Row 1 has stayed as that 1, negative 1, 1, and 4. That did not change at all. Row 2, well, remember, here's my new row 2. It's 0, 6, negative 8, and 2. Row 3, well, my new third row is right here, and it is 0, 3, negative 4, and 3. So we just kind of did 2 steps at one, so we'd have less to write. Well, the next thing I need to do is, again, I need to get this 6 to be a number 1. Easiest way is to divide by 6, but I can't divide by 6, so I need to rewrite this as 1/6 times row 2, and that's going to be my new second row. So if I rewrite this, again, the first row doesn't change. It stays as 1, negative 1, 1, and 4. Now if I multiply the second row by a 6th, 0 times a 6th is 0. 6 times a 6 becomes 1. Negative 8 times a 6th, well, that's going to be negative 8 over 6, and that reduces to negative 4/3. So that's negative 4/3. And then 2 times 1/6, well, that's going to be 2/6, and that's going to give me a positive 1/3. Row 3 did not change. It stays as 0, 3, negative 4, and 3. The next thing I know I need to do is I need to get that 3 to be a 0. Easiest way to do that is to multiply row 2 by negative 3 and add that to my third row to give a new third row. Well, let's do that on the side here. If I multiply this row by negative 3, 0 times negative 3 is 0. 1 times negative 3 is negative 3. If I multiply negative 4 over 3 times a negative 3, I'm just going to end up with a positive 4, because again, if you do this, my 3's cancel, my negatives cancel, you just have 4. If I multiply 1/3 times negative 3, I end up with negative 1. And again, if you look here, negative 3 times a third, well, the 3's cancel, all I'm left with is negative 1. Let's write that third row, and that third row was 0, 3, -4, and 3. Well, if I add that, I get 0, 0, 0, 2. So the augmented matrix I have thus far is 1, -1, 1, and 4, 0, 1, -4/3, and 1/3, and my new third row is this 0, 0, 0, and 2. But this 0, 0, 0, and 2 is a false statement. And since this is false, it tells me that I have no solution. So the answer for number 9 is no solution. All right, let's look at the very last example in the section, example 10. Again, start by writing the augmented matrix. So here I have -3, 1, 1, and then 1, 4, -3, 2, and 2, 5, -3, 1, and 1. I need a 1 in this position. Well, this is the first time that I can't interchange rows to get a 1, so I have to find another way of doing it. Well, notice if I add the first and the second row together, I'm going to get a 1. So I'm going to do the row operation of saying row 1 plus row 2, and that's going to give me a new row 1. Well, if I add those together, we're just going to kind of add them here. -3 plus 4 gives me a positive 1. 1 plus a -3, -2. 1 plus 2 is 3. 1 plus 2 is 3. My second row did not change, and my third row did not change. Then I need zeros underneath that 1. And again, we're going to do that in the same step. So if I say -4 times the first row plus the second row, well, that's going to give -4. That's positive 8. -12, -12. My second row is 4, -3, 2, and 2. Let's see, I get 0, 5, -10, and -10. But I also want to get a 0 in that position in the third row. So if I multiply the first row by a -5 and add it to the third row for a new third row, I get, well, -5, +10, -15, -15. That third row was 5, -3, 1, and 1. Add them together, what do we get? 0, 7, -14, and -14. So the new augmented matrix, first row stayed the same because that one didn't change at all, as 1, -2, 3, and 3. My second row became 0, 5, -10, -10, and my third row became 0, 7, -14, -14. The next step is to get this 5 to be a 1. Well, I can multiply row 2 by a fifth. So 1/5 row 2 for a new second row. My first row does not change. The second row, 1/5 times 0 is 0. 1/5 times 5 is 1. 1/5 times -10 is -2. 1/5 times -10, -2. Third row did not change, so it stays the same. The next thing I need to do is make this 7 into a 0. How would I do that? Well, if I multiply -7 times the second row, add it to my third row, that would be my new third row with a 0 in that position. So let's see here. -7 times this row 2, 0, -7, +14, +14. Adding it to row 3 of 0, 7, -14, -14 gives me 0, 0, 0, and 0. So I ended up with this augmented matrix. 1, -2, 3, and 3, 0, 1, -2, and -2, and then 0, 0, 0, and 0. Well, 0 equals 0. This is a true statement. So this is one of those linear systems that has infinitely many solutions. So since it has infinitely many solutions, remember what we need to do is we need to solve all the variables in terms of z and get that order triple. So what is this as a linear system? Well, it's x minus 2y plus 3z is equal to 3, and then y minus 2z is equal to -2. So start off by solving y in terms of z. Well, if I add that 2z to both sides, I get that y is equal to 2z minus 2. So I have y, z is going to be z, and now I need to solve x in terms of z. Well, I have x minus 2. Instead of y, I write what y is equal to in terms of z, and that's 2z minus 2. And then I have plus 3z equals 3. Distributing here, I get negative 4z plus 4 plus 3z equals 3. I combine like terms. X minus z plus 4 is equal to 3. If you subtract 4, x minus z is negative 1. And finally, if you add z to both sides, you get that x is equal to z plus 1. So the ordered triple solution for this linear system that has infinitely many solutions is z plus 1. Y in terms of z is 2z minus 2. And then remember, z is just z. This is the answer for example 10. That's it for matrices.